We're looking at a series of examples of how to use diagonalization to solve systems of linear ordinary differential equations. So we've looked in the last video at a homogeneous system. Let's look at an example involving a non-homogeneous system to see how it's the same and how it's a little bit different. So we have a 2 by 2 system here. u1 dot is equal to minus 2u plus sine t, and u2 dot is equal to minus 2u1 minus t. So we can see, once again, there's two equations. They're both coupled. I cannot solve one equation for one variable and one equation for the other. Now we have the sine t and minus t terms. Those are the f1 and the f2 that comprise the f vector, the forcing terms. So we have our usual form, u dot is equal to au plus f, where now a is 0 minus 2 and minus 2 0, and then f is the sine t minus t. So it's a 2 by 1 vector, a is a 2 by 2 matrix. The first thing we notice, check the road signs, A is indeed symmetric, so we'll take notice of the eigenvalues and see what that means for the eigenvectors. So we get the eigenvalues, we get 2 and minus 2. Indeed, they're distinct, so symmetric A with distinct eigenvalues. So we expect our eigenvectors to be mutually orthogonal, and indeed they are. So we get u1 is 1 minus 1, u2 is 1, 1. Take the inner product is 0, so they are orthogonal. So everything's going according to plan so far. So we form our modal matrix U. So here's the first eigenvector, the second eigenvector. We will need the inverse of U, not because we have to evaluate U inverse times A times U for the diagonalization, but because we have a non-homogeneous F term, which is going to have a U inverse times that F. You'll remember from our derivation of the new problem. You'll see it right here when we get to it. So the inverse of a 2 by 2 matrix, you just swap the diagonal terms, change the signs of the off-diagonal terms, and then divide by the determinant, and you have the inverse. So we do our transformation from our original dependent variables u1 and u2, to a new set of dependent variables v, comprised of v1 and v2, and the transformation matrix is our modal matrix u. In doing so, we convert the coupled problem in terms of u into an uncoupled problem through diagonalization in terms of v. So we have v dot is equal to u inverse times a times u, which of course is diagonal, times v plus u inverse times f. And this is why we needed the inverse right here. Okay, so we write this all out. I, once again, do not need to evaluate u inverse times a times u. I know it's going to be a diagonal matrix with the eigenvalues on the diagonal, 2 and minus 2. Remember, they're in the same order in which I put the corresponding eigenvectors in to form the modal matrix U. Then we have u inverse times f. So here's our u inverse times our vector f, which is right here, just 2 by 1. And so that gives us this 2 by 1 vector here. So now we can write out our uncoupled system of equations. v1 dot is equal to 2 times v1 plus a half sine t plus a half t. So that's the first equation, and it only involves v1. So regardless of whether it's homogeneous or non-homogeneous, the diagonalization process is the same. It's just that we have a homogeneous form of the uncoupled as well as the original coupled equations. The second equation for v2 is v2 dot is equal to minus 2 times v2 plus a half sine t minus a half t. So I've written those out right here, those two equations. They're, again, fully uncoupled. So now is the new part, and that is, how do we solve these given the fact that they are non-homogeneous? We have these non-zero f's. So now we have our two uncoupled equations for v1 and v2. We solve those using the standard techniques from our differential equations courses, and so we want to get the complementary or the homogeneous solution as well as the particular solution, and those then are summed together, superimposed, to give us our general solution for v1. Same thing for v2. We'll look at v1 carefully, and then I'll just give you the result for v2, and you can check that on your own. The complementary solutions are the same as before. We get rid of these non-homogeneous terms, and we just have our standard equations for v1 and v2. So the solutions are v1 is equal to c1 e to the lambda 1t, and C2 e to the lambda 2t for V2. Lambda 1, lambda 2 are 2 and minus 2. So we have the complementary solutions. We knew what they were as soon as we had the eigenvalues of A. So now let's work on getting the particular solution. So first, look at the non-homogeneous terms and what they contain. We have sines and we have t terms. So we have trigonometric terms and we have first-order polynomials. In that case, the easiest way to get the solution, the particular solution, is using the method of undetermined coefficients. The idea in the method of undetermined coefficients is I know the general form of the particular solution. I know it has to involve, say, sines and cosines and first-order polynomials. I just don't know the coefficients. So we have to find the undetermined coefficients. So this is true for polynomials of any degree. It's true for exponentials, and it's true for sines and cosines trig functions, because we know what happens to them in linear equations. Polynomials stay polynomials, exponentials stay exponentials, and trig functions stay trig functions. Sines become cosines, cosines become sines. So here for V1, let's focus on V1 to illustrate the details. Here is the particular solution. So I know, because I had a sine, that I might need sines and cosines. So I include one of each one with its own coefficient. So a sine t plus b cosine t. Then I had the t term, so I know I have and may need a first-order polynomial. So I use the most general first-order polynomial, ct plus d. Then I just substitute it in the equation, and we need to determine the undetermined coefficients. So this is the v1, and then I differentiate it because I need v1 dot. So I differentiate this. It's a cosine t minus b sine t plus c, because I have v1 dot is equal to 2v1, and then I'll add the 1/2 sine t plus 1/2 t. So here is the v1 dot, 2 times v1 plus the 1/2 sine t plus 1/2 t. Now, to determine the coefficients, I just have to equate like terms on both sides of the equations. So if I look at the cosine terms, I have an a times cosine. On the left, I have a 2b times cosine on the right, and that's it. So a has to be equal to 2b. For the sine terms, I have a minus b is equal to 2a plus 1/2. Then I have, for my t terms, there are no t terms on the left. There's a 2ct term here plus 1/2 t here. And then finally, my constant terms on the left, I have a c, I have a 2d, and that's it. So that gives me my 4 equations for the 4 unknowns a, b, c, and d. So a is 2b, minus b is equal to 2a plus 1/2, 0 is 2c plus 1/2, and c is 2d. Now in general, this is going to be a 4x4 system of linear algebraic equations for our 4 coefficients, a, b, c, and d. In this case, the first 2 only involve a and b, and the last 2 only involve c and d. So I can solve these pretty easily in the current situation. But again, in general, it would be a 4x4 system of equations. So I get that a is minus 1/2, b is minus 10 from these 2 equations, and then from these 2 equations, I get that c is minus 1/4, and d is minus 1/8. So I just stick those in. Minus 1/5, minus 1/10, minus 1/4, minus 1/8 are the coefficients that give me my particular solution for V1. So then V1 is the complementary or homogeneous solution, the exponential, plus the particular solution that we have here, and then that gives us the general solution. So complementary, and then particular. If you do the same exact process for V2, and I would encourage you to do this to practice and to check your results, you'll get this. So here's the complementary solution, and then here's the corresponding particular solution using the method of undetermined coefficients. So all that remains is to convert from the v variable with respect to which everything is uncoupled back to the u variable with respect to which things are coupled, the original variable that we used in our definition of the system. So to do that, we have u is equal to the modal matrix times v. We know what v is. We just solve for those. And we know the modal matrix u. Here it is. and so that's equal to our 2 by 1 vector u. So here's u is equal to the modal matrix times our v vector. And so when I do this multiplication, the 2 by 2 matrix u times the 2 by 1 vector v, I get these expressions. So it's 2 by 1 vector, v1 plus v2, and minus v1 minus v2. I know what those are, I just haven't put them in yet. When I do, I get that u1 is equal to c1 e to the 2t plus c2 e to the minus 2t. So you'll notice I get sum of both complementary solutions plus a combination of the two particular solutions, which gives me minus a fifth cosine t minus a half t. So likewise for u2, I get a contribution from both of the complementary or homogeneous solutions, and then the minus v1 plus v2 gives me 2/5 sine t plus a quarter. Now we weren't given any initial conditions, so I can't determine the c1, c2 integration constants, but if we were, we could, and so we have the general solution here. Okay, let me make a couple comments. First of all, about this method of undetermined coefficients. Once again, the idea is for certain types of forcing functions, f, I know the general form of the solution. And again, that's the case for polynomials, exponentials, and trig functions. I take advantage of that, and all I need to do is determine the coefficients in my general particular solution. So it's by far the easiest way to get particular solutions when it is possible. When it's not possible, you can use the variation of parameters approach that you learned in differential equations. I've given some references here to some textbooks. You'll find this in any book on ODEs. I'd encourage you to go back and read the material on getting these particular solutions so that you're aware of the full complement of tools in your mathematical toolbox. And I want to point out one situation that can arise sometimes that we need to always watch out for. And that is, if there's a term in your particular solution that's already accounted for in your complementary solution. So remember, in this particular case, our complementary solutions or homogeneous solutions had e to the 2t and e to the minus 2t. So if our f had an e to the 2t or e to the minus 2t, we would want to be careful when we formulate our particular solution such that we don't include an e to the 2t, e to the minus 2t on their own. What you need to do is include a t. So you multiply the independent variable t times those terms in order for the process to work properly. Again, all that's in your ODE books. Go back and review that. But you just need to keep that in mind and watch out for that eventuality. Now, there's still a couple of situations that we have not yet talked about. So we looked at a homogeneous example. We've looked here at a non-homogeneous example. We have not looked at a situation where the eigenvalues and or the eigenvectors are complex. So we need to take a look at that. We also haven't looked at the situation where we have higher than first order linear differential equations. So we need to look at both of those, and we will do so in the next video.